command line version of Monster provided as well for your scripting and remote sessions, and you can also save and review these sessions as well. Okay, so the best way to see how to use these tools is with a demonstration. So what we're going to look at is a program called the Noble Ape Simulation. This is written by Tom Barbalet, and he's simulating apes on a tropical island. And these apes can think, and he's simulating the biological environment, so the food and the other animals on the island, and as well as the cognitive processes of the apes. I mean, obviously, simple cognitive processes such as desire and fear and those kind of things. So this is open source, and for more information, please check out his website at nobleape.com. So let's switch to the demo machine. You can see Noble Ape in action. Okay, so this is the map window. Here we just showed, this is the island, right? And each red dot represents an ape running around the island doing its thing. And we can select one ape at a time. That's the ape with the red box around him there. And for this ape, we can see his brain, what's happening in his brain in the brain window, right? And of course, any good performance study requires a performance metric, and our metric is ape thoughts per second. So this is for the original code, we're getting, we have this metric. So around 1,200, 1,300 or so. Okay, so the first thing we'd like to do, we're going to launch Shark, and we'll see what's happening in the system. Okay, so this is the main Shark window, and it's really pared down and simple, just to let you start your work. By default, we come up with a time profile, so this would be the most common thing you'd use it for. We provide a bunch of other built-in shortcuts and configurations. Of course, you can create your own using any of the performance counters. But for now, we're going to use time profile. There's a start button here for starting sampling, but you can also there's a global hotkey so that Shark doesn't have to be in the foreground. It can be in the background, and you can start it. So we'll use that hotkey. We'll take a 5 or 10 seconds sample, see what's happening. All right. So here's the profile. What we've done here, this is just listing the functions that it sampled inside Noble Ape from most sampled to least sampled. So when you're optimizing, you want to work on what's running the most of the time, then you're going to get the most benefit out of optimizing that code. So we see that Noble Ape is 50% of the system. This is the process pop-up, right? And this is like top. It lists what was running in the system. It's kind of strange. 50% of the time, even though we know that we're CPU bound. Well, if we go to the thread pop-up here, you can see that in fact it's single-threaded. So we're running Noble Ape on a PowerMac G5 that has dual 2 gigahertz processors. So all right. So next step, we want to thread this thing, right? Since we want to take advantage of both processors. So this is the heavy view that we're looking at. There's a heavy profile view and a tree view. The heavy view, we can open up these disclosure triangles and see how we got to this heavy function. So we started in main, we called plat cycle, called control cycle, called cycle ape troop, called the cycle troop brain scaler, this important function. So we know our code, and we know that we can't really split the processing of things between simulation cycles, right? The way this app works, there's it does a simulation cycle, and within each ape simulation cycle, it's processing a bunch of ape simulation cycles. Well, the simulation cycles themselves are not independent. They depend on one another, right? But we know that the apes are independent. They're independent thinking apes, so we can parallelize it at that level. We can process the apes in parallel for each simulation cycle. So that's what we did. We threaded that to split up the number of apes. So we have 64 apes, to split it between 2 threads evenly. So you'll note that the brain rate is originally around 1,200. When we do this, we get around almost 2,400, not quite. So that's pretty good. We've got a nice speed up just from threading, from taking advantage of that second processor. So let's profile again and see what's going on. Okay. Right, so now we can see that in the process pop-up, we can see that Noble Ape is taking up a much more significant amount of the system. That's a good thing. And we can see from the thread pop-up that we have our main thread, that's the 9.2%, which spun up 2 computational threads, each about 40% of the time. Right. So the next thing we'd like to do is actually optimize this function. This function is important to us, right? It's almost 90% of the time is spent in here. So if we double click on this, Shark will present us with our source that's been highlighted where we've sampled. So this tells us where in our source code we're spending time. So it's actually inside of this cycle troop brain scalar, it's this for loop. So we can see that this for loop actually represents about 94% of the time in this function. Okay. So I should probably talk about a couple of these other things here. Oh yeah, well, so the scroll bar at the side is like an overview. You can easily jump to the hotspots in your code, right? So it's colored accordingly, right? A brighter yellow means more samples. At the top, we have a source file list. This is, sometimes you can have more than one source file contributing to a particular function with header files and like that. And this function pop-up is like what you have in Project Builder. You can easily jump to different functions. And then we have the edit button. So what this allows you to do is it will jump into Project Builder at the same selected line, right? So you can easily go to where you want to edit and change something once you know where the problem is. Okay, so let's go back to Shark. And what Shark does is it provides us with advice. Well, that's what this little exclamation point button is. This is advice for us. This is calling something out. And so there's 2 bits of advice here, but we'll focus just on the first one. So this loop contains 8-bit integer computation. And obviously, if you're spending a lot of time in this 8-bit integer computation, it might be a good idea to use AltiVec to really improve the speed of this code. So that was what we did. That was our next step. So I guess let's go try that out. All right, whoop. Got to get the rate. Okay, so that's a nice speed up. But we're not done yet. That's good. So let's profile again. Let's see where we're spending time now. All right, so we'll double click again on this. We see the vector function shows up at the top of the profile. And this is the vector code. So if a lot of you are probably, if you've used Shikari, you saw the assembly view. Right, if you double click on any of these, any source line, it's going to jump to the assembly view that you're familiar with. And if you double click on the assembly, it'll jump back. And it's going to highlight the line, the instruction or instructions that correspond to that source line. So you can see, this can give you an idea of how good the code gen is for your compiler, right? What kind of instructions it's generating for each source line. And okay, so if you've seen this before, the columns here, we have samples, how many times we sampled each instruction, address, obviously the address of the instruction, the instructions themselves. You can switch between various views of the address. Cycles is the latency and throughput of a particular instruction. So these are for the 970, right? That's the CPU model down at the lower right-hand corner there tells you that. And in the comment column, various things about this code, and of course the source file at the end. Now, one of the nice things that we give you is an ability to visualize dispatch groups. So if we go to this option, we can turn this on. And we can, so if you remember the diagram that Sanjay showed earlier with the dispatch, we can see here how they, usually between 4 and 5 instructions dispatch this would be in each cycle. So this can give you a good idea of about how things are actually behaving on the machine. So the other thing we provide too is this functional unit and dispatch slot unit utilization graph. So, so you want to talk a little bit to that?
Right. So on 970, as a programmer, the key bottleneck you'll have to face is maximizing dispatch group width, because that's one of the narrower points in the core, because it's 4 instructions wide plus a branch. So what we offer you here in dispatch slot utilization over here on the right is the average group size. You can see how effectively is your code taking advantage of this really wide issue machine, or wide dispatch machine, right? And dispatch defines where instructions are issued to, which functional units. So here you see a map of the 12 functional units that I talked about, and you can see that the units are symmetrical, like the two LSUs here. If there's a big imbalance between, say, one of these, the LSUs, one is doing a lot and one's not, well, that's something that you could probably correct with scheduling or reordering your code, because what you want to do is balance the execution units. Right? You don't want half the chip doing all the work and the other half sitting idle. All of that is defined by dispatch groups, so that's why we've put dispatch group modeling into Shark.
Right, so you can select a few, right? I mean, you can do the
right,
dynamic
sorry.
selection, right?
So this is dynamic. You select a few instructions and it'll tell you where they got mapped to. The charts update and the numbers will update it with it.
Right. Great. So, yes. So this can help you, obviously, on the Power Mac G5, tuning your code. So, but let's go back to the source view. And if we look a little closer at our vector code, you remember we vectorized this inner loop that we saw was taking up 94% of the time, right? Well, now that loop is still important, but it's taking up a smaller portion of the time in this function. We can see also that up at the top and bottom of this function, we're spending more time relatively speaking, in the scalar code, right? The two loops that we didn't touch. So this code is very similar to the other loop. It's almost exactly the same, and I believe Shark will point this out, but yeah. Right, it's saying, yeah, hey, vectorize this loop too. This is important now. So that was the next step, was to vectorize the rest of this, so to vectorize the entire function, and as well as there are a few other optimizations as well. So let's try that out. So we're starting around 10,000 or so. All right, so another 40 to 50% we can eke out by vectorizing the rest of that function.
You can see some of the gorillas have gone off into the water. You can bring them back to life by dragging them back to land. They're a bit suicidal.
Yeah, they just like the beach. All right, so got a 15x or 14x speed up. That's pretty decent. Yeah. We hope you can all do that well in your code too. So the next step, okay, so, no, don't do that. We have a few more things to show. There are a couple other things we didn't really talk about. Shark allows you to manage the sampling session. So we've taken about 4 sampling sessions here. You can either look at these in parallel, right, in a multi-window mode, or you can put them back and deal with them one window at a time. The multi-window mode is nice because you can put them side by side. There's also a session drawer. You can quickly switch between them in the single window mode. And of course, as we mentioned, you can save sessions. There's also ancillary information included. So whenever you take a session, it records what kind of machine it was and gives you some space to write notes to yourself about what was happening on this. So this is archival. You can keep it around, remember what happened. There's also an extensive user guide included, so it's just online here. Please read it. There's lots more information and features that are covered in there. Okay. So one other thing we wanted to look at, we want to use the monster tool, and we want to look at some of these performance counters in depth. So this is the main monster window, and this is the spreadsheet, right? So on the left-hand side, we can see the various performance counters that are on this system. And on the right is the spreadsheet itself. And the shortcut pop-up is similar to the sampling config selection on Shark. Same thing. But what we can do is we can edit these shortcuts. So if we go to the shortcut tab, and we're going to look at DDR memory bandwidth. Right. So this is it's taking a few of the U3 counters, the memory controller counters on this Power Mac G5, and it's going to calculate the number of megabytes transferred over the memory bus. Right. So the way it does this is it counts the number of beats, and each beat is 16 bytes on the data bus. So it can multiply out and figure out for every 10 millisecond sample how many megabytes that means. So we have a session. Let's open that. Desktop. It's on the desktop. Yeah. There it is. Right. So if we pop open the run pop-up, You can see that from this session we have, there were four runs taken. The first was just the original scalar code. The next was threaded scalar code. Then the vectorized threaded code, and finally the optimized vector threaded code. So what we did is we want to look at how this memory bandwidth changed as we changed the code. So we can use the draw chart so we can see this. So remember, we took 100 samples total, so 25 samples for each type of test. So originally, we can see that, obviously the memory bandwidth it varies over time a little bit, but we're around 250 megabytes per second for the original single-threaded code. When we threaded it, we're using closer to 400 megabytes per second. Then AltiVec can use a lot more of this bandwidth, around 1250, say, megabytes per second at average. And then finally, the optimized code, 1700 megabytes per second average. So you can see how, as we optimize the code, we were able to take better and better advantage of this bandwidth, the massive bandwidth that's available on the PowerMac G5. So, okay, let's. All right, so let's go back to the slides, I think. Right. All right, so you might wonder, I guess, I'll let Sanjay talk.
Yeah. So you might wonder, how does this compare against G4? So we started out with the regular scalar code, right? And on the G4, you get about 1,200 ape thoughts per second. And we were getting closer to 1,300 on the G4. Well, you say, well, the G4 is running much higher frequency, but we're barely getting a little more than 10% faster performance here. So what is the bottleneck? Well, the initial bottleneck was all integer performance. So with the longer latency, longer pipeline instructions, you're just not going to get the full frequency increase in your performance increase. So when we went to threaded, we started to expose the better bandwidth on the bus. So because we have two processors and they each have independent point-to-point connections to the memory controller, now you can see we're over 20% or so faster than the G4. And then we really break this open when we go to vector. Right? The G4 does well, right? We get a 2.5 or so x speed up from using vector. But on G5, we don't have any bandwidth limit yet. So we get a full 4x improvement from going to vector. And then with vector optimized, you can see again, the G4 does pretty well, nice speed up. And the G5 gets a 60% speed up. And that's, if you look at back at that monster chart, you can see we were getting peak bandwidths of 2.5 gigabytes a second on the bus. So we're still not done yet, but we didn't have more time to optimize before this demo. But clearly, there are a lot of resources there. And if you start with basic code, well, you might get a decent speed up over a G4. But if you put a little effort into it, you can get very big speed ups if you take advantage of AltiVec, take advantage of all the bandwidth that's available to you.
Right. Okay, so a third tool we'll talk a little bit about